So what we're going to do is pretty much take everything from Chapter 2, repeat it with today's slides, and then look at the more advanced application thereof. So if we take any amino acid, what you should be able to do is work through or stepwise attempt all the way through the different states that could possibly be available to it when you change the pH. When you change the pH, you're changing hydrogen ion concentration. That can have an effect on the structure. Okay, so what I asked you guys to do on Tuesday was to take tyrosine and look at all of its individual states. How many of you actually did that? Kind of what I thought. All right. It is important to go through and process this. If you aren't working on it, it is going to become very, very challenging to go through and do the exams, okay? Because you are expected to be able to do all of these things. So what we're starting at this case, for this structure, horribly drawn, we need that hydrogen there, which makes me nervous about what I've got revealed underneath. What pH do you think we'd be at for this one? Should be very, very low pH. Okay. Why low? I don't see any hydrogen ions, so I don't quite accept that. This functional group is a carboxylic acid. If it's going to have a hydrogen on there, we have to be at a very, very low pH, because that species acts as an acid. So at non-low pHs, it's going to donate that hydrogen off. Okay, so we have to be at an extremely low pH. Okay. The next point would then be, well, what hydrogens are acidic in this structure? Well, one we just identified on the carboxylic acid. So we've got to be a little bit careful. You said any of the OHs. Any of the OHs in this structure I would accept. Okay, so that H is also acidic, but it's not because it's an OH.
Which one did you just draw?
So I'm highlighting them in red. So
Okay.
we've got the red for our carboxylic acid, which was a typo that should have been on the structure.
Right.
Then we've got the red down here on that OH. Okay. Why is that second OH, the one off of the oxygen that's not on the carboxylic acid? Why is that one acidic? Kind of, sort of.
Doesn't have resonance.
The structure as drawn isn't going to have any resonance, or at least reasonable resonance. Okay, but that's not what we're concerned about. If we're looking to see if something is acidic, what do you need to look at? You can kind of look at electronegativity, but if I went through and drew this structure, this hydrogen is not acidic. Whereas the one that we've identified on our structure is acidic. Polarity is way too vague of a term. It should never be used in an undergraduate class. It's a horrible, horrible term. It explains nothing. Okay, particularly because, and I'm not blaming you, that's just how it gets taught, because the OH up here is just as polar as the OH down here.
Induction? I'm just starting out terms now. Induction effect?
So let's go back. If you have an acid, why is it an acid? It donates proton. So if we look at a general reaction for an acid, we have H plus and A minus, right? For this species to be an acid, what has to be true? It has to give up the hydrogen. But all structures that have hydrogen attached to them, we could draw this reaction. Right? So that doesn't help. Anything that has hydrogen attached to it, we could draw this system. And we could go through and draw all the hydrogens off of those rings. Those hydrogens aren't acidic. Why are the hydrogens on this oxygen acidic? Okay, so it goes back to our definition of an acid. Yeah, it has hydrogen, but that's pretty meaningless. Okay, what's the other part of this equation that is of critical importance? It's still recording, look at that. So as a hint, let's work our way through this. HA, present for everything. H plus, present for everything. Okay? What's the only thing left? A minus. If HA is a strong acid, what does that mean about A minus? It must be not even just a weak base, it must be stable. If A minus is unstable, does this reaction occur? No. A minus must be stable. What is A minus? The conjugate base. How do we evaluate stability of a conjugate base? Then you're using the reverse logic back to where you started, and that doesn't help you out.
If it's a halogen and it's a strong acid, then its conjugate would be weak.
Why are halogens strong acids? They generate Cl minus, Br minus, I minus. Why are those species stable conjugate bases?
They form together like BR2.
Atomic mass or electronegativity?
It's not reversible, it's not a reaction.
Compare carbon to bromine. We've got two periodic tables up here.
Bromine is larger.
What was that?
Bromine is larger.
Why does that matter?
And,
We're looking at a negative charge on that atom.
Electrons?
Okay. If I put an electron on that atom.
That's what I said, atomic size.
Oh, I'm sorry I said that. I didn't hear you.
I'll say electronegativity.
What's the reactive part in both of these species?
Electrons.
The electron. The electron hurts. Okay? Hurts a lot. Okay? Let's say it kills you. Okay? We've got these two pools here. I'm going to give you a choice. Stick your hand into one of them. Which one do you stick your hand into?
Carbon?
Remember, if you touch the electron, you're dead.
Oh. I thought it was a smaller pool, so it's safer. Bromine.
The electron's the exact same size. You stick it in the bromine. Why?
less chance of
Less chance of hitting that electron. If we give the electron more space to move, it is less reactive because there's less chance of encountering it. The electron is what causes a reaction. So what's one thing that we could do to evaluate acidity? We look at the stability of the conjugate base. The bigger the conjugate base, the less reactive the negative, which then means what about the stability of our negative? It becomes more or less stable if it's less reactive. More stable. If our conjugate base is more stable, what does that say about the acidity of this compound? It's very acidic. So all of our halogens are great, or most of our halogens are pretty strong acids. Chlorine, bromine, and iodine are all strong acids by definition. Why? Because they're massive. They can stabilize that negative charge. Okay? But if we compare HF to O, or actually let's stick with the carbon. Now what happens when we move to fluorine? Well, the size of fluorine, for all intents and purposes, is the exact same as carbon. Does the size argument work anymore? No. So there has to be something else affecting this. Well, maybe. Is there a difference in acidity between HC and HF?
Electronegativity.
As far as acidity goes. What's the acidity of HC? No. What's the acidity of HF?
Yes.
Yes. So clearly there is a difference here. We have to find that difference. It's not size. What's our difference? Okay, so if we again look at our reactions, is our difference easily seen up here?
yes.
Okay, what's the difference you see up there?
Yeah.
Right? Does that, no, that's fine. That's a fair difference. Does that tell you anything about the acidity? No. So does that help you? No. Particularly because how did we decide that we have a strong acid? Hydrogen bound to any atom looks like hydrogen bound to any atom. There is no energy difference there. Where does the energy difference show up? Does it show up as H+?
No.
If it's acting as an acid, H+ is consistent across the board. It's always there. Always. So that doesn't help. What do we have to evaluate? Conjugate base. Why do we evaluate the conjugate base? It's charged. Charge is inherently bad. That's why you don't stick your finger in the electrical outlet, because what's coming out of the electrical outlet? Charge. Right? So we don't do that. We need to stabilize that charge as best we can. One option was put it on an atom that's really, really big, because if it's really, really big, that electron can move across a larger area, and the charge to size ratio is very, very small. So our effective charge becomes nothing. We don't have that size difference here. What else could we evaluate? Because you've already told me HF is an acid, and this one is not.
Electronegativity.
What does electronegativity measure?
The polarity, well, we can't say polarity like you said.
No.
Like the attraction that the atom has to the electrons around it.
Close, not quite. Electronegativity is a measure of an atom
It's affinity
grabbing
to-
electrons, but it's a very particular type of electrons. What are you going to say, Jamie?
No.
To stabilize it.
We can discuss that in a little bit, but not quite. Electronegativity is the ability to hold bonding electrons. What does that mean? Fluorine, in comparison to carbon, is more willing to take the electrons away from the hydrogen because it is more electronegative, which means which of these cases is most likely to happen? Fluorine. Because it's already taking those electrons because it is electronegative. Okay? Which then says if this species, F minus, is more likely to happen, which of these two is the stronger acid?
Hydrofluoric acid.
Hydrofluoric acid. Because I have a larger concentration of this, which means, what's my concentration of H+? If I have a larger concentration of this relative to here, what's my concentration of H+ relative to here?
Larger.
Okay. Where did F minus come from? Came from HF. If I have more F minus, where did that F minus come from? HF. What happens to the concentration of my H+?
Down.
It must increase. It can't go down. Where did F minus come from? HF. So if I'm going from HF to F minus, what also has to be produced? H+. Okay? This is a massive aspect of organic chemistry, is looking at these acid-base definitions and understanding something about them. When we move to biochem, you either have to have all of that information memorized, which I'm not going to lie is questionable at this point, or you have to memorize all of the possible acidities for every single amino acid. Okay? So you have to understand or you memorize. And as we'll see in a few slides, there's a lot of memorization associated with the amino acid acidities. Okay? 20 amino acids. Most of them have just 2 acid functional groups. Okay? Some of them have 3. So if we just say 2.5, well, it's not even 2.5, let's just say 2. That's 40 acid functional groups you need to memorize. Okay? Because you have to be able to look at these structures and predict that reactivity. Okay? I didn't tell you you have to memorize them all, but if I give you the structure, you need to be able to tell me where the acid is, where the acid isn't. Okay? That is your responsibility. That is a carryover from organic chemistry, not biochemistry. Okay? And if you've got problems with that, you need to talk to me and we need to work through that and make sure you can understand where your differences are. Okay? Which brings us to our next issue. If we remove the hydrogen from here, what's our conjugate base look like? O negative. If we remove the hydrogen from our ethanol, what's our conjugate base look like? O negative. Is there a size difference between oxygen and oxygen? Is there an electronegativity difference?
No.
What's the next thing? Has to do with the next atom, sort of. What about the next atom? What are we going to be looking at?
The bonding, the forces.
The answer to all things organic chemistry. Resonance. What can happen with this ring? I can take electrons from here and I can move them into the ring. What does that do to the charge? Distributes it over what?
The entire ring.
The entire ring. So now what happens to the area? The size where my electron is located. It's dispersing it, so it's getting bigger. What was our very first thing that we evaluated? Size. Resonance is size. The bigger our atom is, the more acidic it becomes. Resonance is now saying I can't change the size of the atom, but I can change where the electron is located. Effectively putting that electron over a larger area. Resonance is the exact same thing as size, except resonance is over a molecule, size is over an atom. So we look to our atom effects, then we move to our molecule effects to determine acidity. If we take a look at our ethanol, there is no resonance option. If there is no resonance option, where does that charge stay?
Oxygen.
On the oxygen atom. With the case of our ring here, where can the charge be shifted? It can be on the oxygen, it can be on that carbon, it can be on that carbon, and it can be on that carbon. I've now taken that electron density, and instead of it being located on only one atom, I've spread it across 4, which does what to the relative charge? Bigger or smaller? Smaller. Right? If it's less charged, what does that mean about its stability? More stable, which means what about the acidity?
Less acidic.
Careful. This species is more stable.
No.
If we cross the
Less
arrow,
stable.
we're now saying that this species becomes
Less stable. More acidic.
less stable, more acidic. This functional group is acidic. So what's your memorization thing that you could have done? Put my pen. What's the name of that functional group?
OH?
Nope. Well, that's part of the question, is figuring out which one. What is that functional group there?
Oh, is it phenol?
Phenol.
Yeah, you got to be careful with the pronunciation, but yes. We're looking at a phenol. It's not OH, it's phenol with the whole piece. What's special about phenols? They're relatively acidic. Okay? That comes back to now our chemistry that you should have picked up in organic. Okay? Some of that comes from just the practice of having to go through and do all of that organic, which may take a full 2 years or 2 semesters to pick up. If you only had 1 semester, your experience with it gets very weak and you have a hard time picking it up. So the stuff that you talked about in organic builds in biochem. If you have a weak foundation, you're going to have a weak time in biochem as well. Okay, so go back and review that material if you need to. Okay, so we now have 2 acidic hydrogens. I'm going to erase all that phenol information and everything else. Okay, how many reactions do we predict tyrosine to have? As a hint, if we drew out this structure again right here, it would probably take up that whole space. How do I get to that space? I probably added an arrow, right? And if I did 2 reactions, I added another arrow, and there's another space. So I only did 2 reactions. I probably drew a couple extra boxes. That seems a bit odd. So how many acidic hydrogens are there in tyrosine?
3.
There's 3. Okay. How do you know that? 2 options. 1, I'm trying to allude to that information by giving you those boxes. 2, I told you to do this. That was one of your homework assignments, was to do this Tuesday night. Okay. 3, you memorized it because you looked at the pKa's for tyrosine and there's 3 of them, which means there are 3 acidic hydrogens. Where's that 3rd acidic hydrogen? One of the hydrogens on our NH3. So now what we've got to do is stepwise through the removal of those hydrogens, and we would remove them at the appropriate time. What do we mean by the appropriate time?
More acidic.
Which one's more acidic? How do we know acidity?
pK.
Good answer. pK is going to be the easiest. The hard answer is going back through what we just worked through. Okay, looking at the stability of the conjugate bases, and you'd have to evaluate all 3 of them to decide how it balances out. Or you can look up the pKa's. Okay. All amino acids have which two compounds or which two acid functional groups in common? I'm going to be a little bit careful about calling it the carboxylic acid. You're right. It's this acid functional group, and it is often referred to as the alpha carboxyl. That's an H there. Why is it the alpha? Because in amino acids, that carbon that I've now dotted is the alpha carbon. Right, why do we call it the alpha carboxylic acid? Because it's the carboxylic acid attached to the alpha carbon. Right, why is that important? This side chain, our R group, could very well have a carboxylic acid on it. If it does, I can't just call it the carboxylic acid being in common, because the R group is different from the backbone of our peptide. Okay, so you'll see that alpha symbol show up. What else is in common with it? All amino acids. The amine. Be a little more detailed. What was that? It's the alpha amine. Okay, why do we have to say the alpha amine? Because again, the R group, our side chain on our amino acid, could have an amine group on it. So we want to be clear that when we're talking about the amine functionality from our backbone of our peptide, that it's the alpha amine, not the R group amine. Okay? Just because there's been some questions about this, we now have our alpha position located. What comes after alpha?
Beta.
Beta. Where's the beta carbon?
Down the chain.
Down the chain following our R group. Okay, so we can't just say it's the carbon next to it because there's a carbon next to it on the carboxylic acid. Okay, that won't be specified as the beta. The beta is going away from the main chain into our R groups. What comes after beta? I always get it wrong too. I think it's supposed to be gamma. So it goes alpha, beta, gamma, delta, epsilon,
And then W.
and then officially you can go all the way through it. One of the last things you'll do with the long carbon chains is you may see this, it depends. They'll refer to the last carbon in the sequence as the omega. Why? It's the last letter of the Greek alphabet. I'm the alpha, I'm the omega. I don't know where that's from, but that sounds familiar. Beginning and the end.
Scripture.
Oh, it's scripture? Oh.
Bible.
God said that.
See my background. So, we've got all those common acids. If we want to decide what's going to happen first, we could evaluate our pKa's. The alpha carboxylate usually has a pKa sitting about 2. The the alpha amine has a pKa sitting of about 9. The phenol functional group is part of your side chains.
It's like 10.
That's where that one gets a bit dicey. Okay? I've usually got it memorized at 10.
It's a little-
You're going to see some side effects because of the rest of those electron withdrawing groups, which can potentially affect this. That puts the 9 and the 10 very, very close to each other. So what would we do to ensure that we got this structure drawing right? We could try that, but you're looking at an electron withdrawing effect that you can't, it's not going to be easy to see, quite frankly, unfortunately. There's a nifty table in your book that lists all the pKa's. Just look up the pKa's. Make sure that you're getting it correct, particularly as it pertains to homework. If it was an exam, I would give you the pKa's because I don't expect you to have them memorized. Okay? There are 2 that you notice that I already had memorized. The acid, the alpha acid, and the alpha amino. Why?
Use it all the time.
You use it all of the time. Okay? And for every amino acid, they are roughly 2 and roughly 9 for every single one. So when you scan through that table, you'll notice they are very, very close to 2 and 9. So I spent the time to memorize that information. I didn't spend the time to memorize all the art. Well, I did have to for my class. Right? And we'll see why that becomes important with what could potentially be asked on an exam a little bit later.
But there's only a few of them that have that second.
There's only a few. I think it's 5 or 6. Yeah. It's 7?
Is it
Fine.
really?
So it's 7. That's pretty darn close to half, if you ask me. Okay, so what we would now go through and do with this pK information, which one of those is the most acidic? Our alpha carboxyl is the most acidic, so what should we do to move from here to here?
Take off the hydrogen.
Remove that hydrogen. What should we do to the rest of the hydrogens? Leave them alone. Okay, so I didn't stepwise it. Okay, well, here, let me real quickly adjust that. We're just going to skip real quickly through it. Animations.
So in
Come back
each of
here.
those titrations, you're just removing
Disappear.
one hydrogen?
You are just removing one hydrogen.
Okay.
Okay? And yes, each of those acidic hydrogens does have an effect on the other one, which is why their pKa's vary from just the standard functional group. So, assuming I did this right, which looks promising, we start with pKa 2. We remove just the carboxyl, our alpha carboxyl hydrogen. We move to the next acid, pKa 9, which we said was the amine. We remove that hydrogen. pKa 10, we remove the last hydrogen. And look at that. 2.2, is that exactly 2? No, but for all intents and purposes, that's pretty spot on. I said 9, 9.11. Not exactly right, but it's close enough. I happen to remember the pKa of a phenol group being about 10. Okay, I don't expect you to remember that. That comes from experience in organic chemistry. Okay, so some of those basic functional groups, okay, which you should have been told in organic chemistry, if you know your functional group pKa's, it becomes helpful. Here's where it becomes helpful.
Are these pKa's before you take off any of the hydrogens, or are they?
What is the
subsequent?
pKa reference? It's
Oh,
the removal of that particular hydrogen. How acidic is that hydrogen? So a pKa 10 is in reference to this hydrogen. But it's looking at the reaction between this species and this species. Okay? It's the Ka of B over A, now the negative log of that. Okay, so it's in reference to the reaction. The pKa doesn't say anything necessarily about what species, it just says the reaction balance is what you're looking at with the pKa. Okay? Other question, what's up here? Does anything interesting happen to the, oh, sorry, go ahead.
If the pK of the phenol group was less than the pK of the amine group,
Uh-huh.
which one would have come first? Will the side chain reaction happen before?
So our pKa's are ultimately telling us which acid reacts. If our pKa is lower, we'll remove that hydrogen first, which is why our very first reaction removed the carboxyl, because it had the lower pKa. It was more acidic. If the side chain pKa was a 6, then it has to come before the alpha amino, because it would be more acidic than our alpha amino. And that happens. Okay, you will see that happen. So it's different for each of these amino acids. Take a look at the structures. Notice anything as we compare these structures all the way through. You may not, that's fine. What was that?
charge?
What about the charge?
Overall.
What's the overall charge on our first structure?
Nothing.
What's it become?
Nothing.
Oh, that's right. Let me fix that first structure, because there was that typo. We needed that hydrogen there.
Yeah, so it's actually plus 1.
So plus 0.
Plus 0
Minus. G minus.
and minus 2. The charge changes as we change the pH. Would that potentially affect how this molecule is going to interact with other molecules?
Yes.
Yeah, it has a massive effect on it. So as we change the pH, we can look at massive changes in the overall contribution to our structure of our protein just because the constituent pieces of our protein will change. Which means we need to know what happens to it. So one of the things that we'll do is look at that charge distribution and see how it affects potentially our overall structure. Okay? More often than not, what people will zero in on will be this structure. Well, actually, let me box the whole structure. We'll zero in here. Why there? It's neutral.
That's the intermediate.
right? So the neutral state is going to have arbitrarily our most neutral state. So we're just kind of focusing around that. So what we would want to do is look at potentially all of our amino acids and say, at what point are they neutral? Right? That point is the isoelectric point. When do they all have a zero charge? Right? How can we go through and evaluate that point?
Add your two pKa's from one to the other and divide by 2.
What we're looking at is the exact instant that we have just this structure. That exact instant is going to be the average of those two pKa's. Okay? So we'll look at our 0 point for every single one of our things, and that 0 point, we look at the pKa's around it and average those two pKa's. That gets us to our pi. Well, in this case, what we've got is 3 pKa's. That's a more challenging question. What if there were only 2 pKa's? It's easy. We just average those two. I don't care about the structures because it's only 2 to average. It's got to be those two. Okay? So this is definitely the more challenging one to identify that pi. So now that we understand something about what's happening to the structure, we get to go through and deal with a titration curve. So, where do you want to start?
Top to bottom.
What do you mean top to bottom? I don't know what that means.
Instead of the high.
Okay, so,
Start from the basic solution and then work our way down.
okay, that's absolutely the hardest way to do it, but we can do that.
Well, what if you do
I'm
that?
fine.
What if you do that on the test?
I won't. So, it ultimately doesn't matter however you do it, but either way, you still didn't give me enough information to start it. Okay? Because I can start basic here, and I can start basic here.
Yeah, right.
Okay? So, I still don't know where you want me to start.
You say top right?
So where do you want me to start? Okay, bottom left. I'll accept with that. So what we're starting with down here is no base added. Okay? And we should be starting at a low pH. Why a low pH? Because there's no base added. Okay? So the structure that we would then have at this point, if we go through and label these, we'll call it 1, 2, 3, and 4. What do I have at this point? Okay, I don't care about charge yet.
Your pK is
What
2.
structure do I have? I have structure 1, the most acidic form. If we went back to the buffer thing that we did with the acids and bases, we said we started with HA. Well, what are we starting with here? Officially, we're starting with H3A, okay? But I don't want to draw all that. That's why I labeled them as 1, 2, 3, and 4. So we're at 1. What happens when we add a little base? Okay. I should now start moving along that base axis. But what do I do on the pH axis?
Slightly.
Why slightly?
Because you have a lot of acid and very little base.
This species is acidic. What happens when I add base? It reacts with the acid. What happened to my base? It disappears. Well, if there's no base, should the pH go up by much? No. So what I would expect is a relative kind of flat line coming off of this, until eventually what happens?
You get to your PI of the.
No PI. Go simple. I'm getting to the equivalence point. What does the equivalence point mean?
Have 50% of each.
Yeah.
Careful. That's the half equivalence.
Yeah.
The first acidic proton is completely removed.
I have completely removed the first acidic proton. So now I add that one molecule of base. There's no more acid to react with it. So what happens to pH? Spikes violently upwards. Okay, so what I would expect to see is now a spike. Okay. If that was the only proton on there, it should spike violently upwards until I hit roughly
Base.
pH 13, extremely basic. Right? Is that the only hydrogen on this structure?
No.
No. So what happens?
You're gonna hit another.
It spikes violently upward, but then it plateaus. Because there's another acidic hydrogen. Okay? And then eventually what happens is I continue to add base.
So hydrogen goes away.
I've lost now the second hydrogen. So it's got to spike again. Okay? If it was only those two hydrogens, that's going to spike and level out roughly at the pH level of just base, which should be about 13. Okay? Do we have another acidic hydrogen? Yeah, so what happens instead?
See it plateau again.
It plateaus again, till eventually
It spikes.
it spikes, and then it'll level out finally where we're just strictly base. So we should have 3 spikes within this. Those 3 spikes corresponding to the 3 acidic hydrogens. Okay? So now let's start to add some more information into this. And I'll put in my new information in different colors. So we got 1, structure 1. Now at this point, blue dot in that first spike. What species is there? Okay, there's lots of information you could write there, but you should be able to tell me a single thing. It is not 50% of both. Because remember, the reason why the pH spiked was because there is none of that.
So 100%
Sort of. You got to be careful. What do you mean 100% base? 100% of the
conjugate.
conjugate base, which is structure 2. What happens at the next spike? I'm now shifted to structure 3 because I've now completely removed all of structure 2 and converted it into structure 3. What happens at the next spike? I'm now at structure 4. Just to be obnoxious, what species do I have out here? Just structure 4. I can have more base, that's fine, but I don't care about the base that I'm adding necessarily. I care about those structures, because that's what I'm running the experiment on. So as soon as I clear that last hump, all I've got is structure 4, everywhere on that last section. Okay, I can't have any of the other structures because I'm too basic.
So that's 4, then it spikes, but then it levels off because...
It levels off because we're now at the capacity for the solution to be basic. So if you take a concentrated hydroxide solution, its pH is roughly 13. So it can't get any higher than that. Or yeah, it can't get any higher than that because you can't put any more hydroxide to remove acid. You've reached the saturation limit of water.
It's not at that equivalence point either. So what's leveling it off from
The capacity for water to hold hydroxide. That's what's leveling it off. You can't continue to go if you can't physically add more hydroxide to the solution. How can your concentration of hydroxide go up anymore?
Yeah.
If you can't put more in, your concentration can't change. So it will level it up at that peak, which is somewhere in that 13 to 14 range. Okay? So what you're looking at is the capacity for water. It now has nothing to do with the species that we added. Okay? So we now know where our structures are. And as you guys started to allude to, you wanted to look at something about these points where you had 50-50. Okay, well the 50-50 is 50-50 of what? Our acid and our conjugate base. Which acid, which conjugate base?
Depends which one you're looking at.
Depends where we're looking on the curve. Okay, if I'm looking up here, if I want to look at the 50-50 between these two, I'm concerned about structure 2 and structure 3. I don't care about structure 1 because it's not there. Structure 1 has completely disappeared and become structure 2. Okay? So if I'm now looking at my half equivalence, I'm looking at what point is my concentration of 1 equal to my concentration of 2? It's going to be halfway in the conversion to all 2. Well, that halfway distance is based on how much base I added. So what I'm looking at now is half of this distance. Well, what is half of that distance? Somewhere in the middle here, we're looking about that, which means I could draw across to the pH. What do I know happens at that half equivalence point? pH equals the pKa. Okay? We can add more information to this. We can actually say what that pH is. Why can we say what that pH is? We know the pKa is 2.2. Okay. What happens for the next value? When I look at between 2 and 3. When am I halfway between 2 and 3?
Halfway between 2 and 3.
And I know, and that sounds kind of weird, but we have to be very careful with that. It's halfway between 2 and 3. Not halfway between 3 and 1, because 1 isn't present at that half equivalence. What I'm concerned about is the halfway point between the acid and the conjugate base. Well, the acid at this point is 2, not 1. So halfway now puts us here. At that orange point, what do I know? I can come up with my pH, and since it's now the half equivalence for that second one, I know that my pH is equal to my pKa. Do I know what the pKa is in this case? What is the pKa? 9.11. So you can tell I did this perfectly symmetrically and to the proper scale. Thank you. Your laughter is kind. If we move to the next one. Okay. We move, that's why I didn't put any numbers on the side. We move to the next half equivalence point. I don't care about 2 because is 2 present in this place? No, I only care about the halfway distance between 3 and 4.
What is true about the concentrations at the half equivalence point if pH equals pKa?
I'll come back and add that information in. Give me just a second. Let's finish this last part out. I probably should have started with that, but I've already committed. We know again the pH equals the pKa. Do we know what the pKa is? Was it 0.7? 0.7. I've now added a bunch of this information in. How did we know the pH was equal to the pKa? Okay, so you got a couple options here. You can say, well, it's the half equivalence point. I don't really like that answer. Try again. What's it coming from?
Half of the conjugate base is equal to...
Yeah, so it has to do with our concentrations of our conjugate base and our acid being equal to each other. That's true. So we could tag that information in there. The concentration of 3 equals the concentration of 4. For this one down here, the concentration of 2 equals the concentration... I already forgot 3.
But essentially, isn't it like 1 or 0 or something like that, so that when you calculate it out... in the
I know what you're thinking.
calculation,
I know what you're thinking.
It comes out to be equal, the pKa is equal to the pH.
What calculation?
It's the pH, yeah, Henderson has one.
There it is.
pH equals pKa.
pH equals the pKa plus the log of A minus over HA. So at the half equivalence point, I know these concentrations are equal to each other. Well, 2 was A minus. 1 was HA. So if those concentrations are equal to each other, what? That should be HA, sorry. I think I got too excited and started drawing the bracket instead of the H.
The log of 1 is 0, right? So,
If those concentrations are equal to each other, I don't care what the concentration is. 50 over 50 is 1. 50 billion over 50 billion is still 1. So what's the log of 1? 0. That term disappears. What's left? pH equals my pKa. Okay. So the Henderson-Hasselbalch equation gives you all of this information. Okay. If we now want to think again about the PI, we'd have to go back to our structures. Where did we say it was neutral? It was neutral for structure 2. So what we are looking at is the point where I have a neutral structure. So where on this graph do I have just structure 2? Pointing kind of works. If you can give me some description. The first equivalence point right there. That's where structure 2 exists and only structure 2. Okay. Well, what is the pH at that point?
It's halfway between 91 and 91.
It's halfway between our first pKa and our second pKa. Now I know the pH when my structure is 0 or has 0 charge. That 0 charge is then defined as the pi. Okay? So looking at a curve, we can't determine the pi. Right? Because anywhere on this curve does it say anything about the charge of structure 2 or structure 1 or structure 3 or 4. That information's not there. The only place you find that information is by going to the structures. So you need to have some understanding of the structures to really come up with the pi. I will tell you that your textbook, okay, and this is the harder one because we've got 3 pKa's to worry about, so we have to pick the proper 2. If you have just 2 pKa's, your pi is always the average of those 2 pKa's. Always. Okay. With 3 pKa's, you have to be very careful about which 2 you average. Because if I average pKa 1 and 3, do I get the right answer? How about 2 and 3? Okay, no, that's going to put the averages in different spots. Okay, so you have to make sure you average the proper 2. The textbook comes up with some weird, goofy explanation that I've never been able to understand. Okay? Push it further. I don't blame the textbook on this, because I've used other textbooks. I've heard other people's explanations of it, and none of it makes sense to me. Okay? If it's a basic side chain, then you average the first and the second. If it's an acidic side chain, you average the third and the fourth. I've gone through, and it's inconsistent at best. Right? If I can't trust somebody's method, I'm not going to use it. The way it works, find where it's 0, overall charge in the structure, average the pKa's around it. Okay? That'll get you the pi.
That's the easiest.
So,
Easy is relative because that involves a lot of structure drawing,
Sure.
which I'm fine with. Yes.
so
Sorry.
I'm looking for the PI between 1 and 2, I'm going to average 1 and 3.
I'm going to average pKa 1
Right.
and pKa 2.
Okay.
Which is, so we have to, I guess, be careful on that. When you say 1 and 3, what do you mean? Structure 1 and structure
Yeah.
3? It's
No,
not that.
You're correct, I actually meant the PKA points, that's right.
So it's the pKa 1 and the pKa 2.
Okay.
If we average pKa 3, your average comes in somewhere up here. That's
Yeah.
not the proper pi. Your pi is down here.
Okay.
Okay?
So you're gonna give us the structure so we know what the PI would be, so that we know which.
I would give you an example structure, and I would give you all the pKa's. Okay, undoubted. So I could ask it I would probably ask it 2 ways. I'd give you a structure of an amino acid that just had 2 pKa's, ask for the pi. That one, everyone should be able to do that one. And then I'd also give you a structure with 3 pKa's, and then ask for the pi. Okay. With that one, you need to draw out all the structure, or all the structures for that one, to figure out where it's neutral, so you know which pKa's to average.
But we'll have the PKAs.
You will have the
So much
pKa's.
enough, okay.
Yep. Questions? Okay, so this is what we're talking about with our isoelectric point. It's the point at which there's no net charge on the molecule. Okay, so we look at the whole thing. And that's where I said it's typically just the average of your 2 pKa's. So for, on this table, glycine through proline, I have a hard time lining this up. I don't know if anybody else does. If you have a hard time reading this graph, you should get a sheet of paper and line it so that you can make sure you see them accordingly. Because you do have to run calculations in the homework, and if you miss a line, you're going to get the wrong answer. Okay. So glycine through proline, those PIs are easy, because there's only 2 pKa's. I just take the average of those 2 points. What's that value going to be for each of those?
The PI.
It'll be the PI, yeah, fair enough.
But they're neutral at that point.
They are neutral at that point. What's the value for glycine's PI? We say roughly between 2 and 9, 6 and change. What's the PI for alanine? Roughly between 2 and 9, 6 and change. What's the one for methionine? Between 2 and 9, it's roughly 6 and change. So pretty much 13, I think is what, because you said there were 7. 13 of your amino acids have the exact same PIs, okay, within error, because again, your pKa's slightly change. Okay. The other 7 are going to be your challenging ones, because those have 3 pKa's, and you have to make sure that you average the proper pKa's within them. Okay. That's where, again, I say use your structure. Okay. So one option, so I pulled this one off the internet, which is apparently from another textbook. We've got all of this information now summarized. You've got the amino acid names in alphabetical order in this case, the 1-letter codes, the pKa's for each of those, and the PI. Okay? Theoretically, these PIs are correct. Okay? Again, I have a low trust for anything within biochemistry, so I would check those values just to make sure they came out. So I think I checked a handful of them with the method that I used with the structures and consistently hit the right spot. Okay? So you're responsible for determining your PI. I will give you pKa's, though you should still have the alpha carboxyl and the alpha amine. You should commit that to memory just because it's easier. You don't have to look those up. You need the 1-letter code for 5. You need the 3-letter code for 5. You need the name for 5, and you need the structure for 5. Okay? And only 5. In a more advanced class, you have to have all of that information memorized. You have to be able to process it all, because on an exam, they don't want to give you all that information because they're freaking lazy. Shit. Just recorded that. Okay? Other things that you can go through and do is remember when we had that deal with what species is present at a particular pH? You can evaluate that back to your pKa's. So we've got these approximations that fall out of the Henderson-Hasselbalch equation. So in the chapter 2 homework, I had you do a bunch of calculations with the Henderson-Hasselbalch. You could have done those calculations, or you can kind of cheat and just say if the pH is less than the pKa, then I know I have HA as the species. If the pH is greater than the pKa, then I know I have A minus. Okay? And you don't have to go through and use the Henderson-Hasselbalch all the way through. Okay? Questions? I know this is exciting stuff. General amino acids basics to remember here. Okay? We've got 20 amino acids. We'll refer to them as alpha amino acids because we can have other structures that have both an amine and an acid, but they have more than one carbon in between, so it's not officially an alpha amino acid. 19 of 20 are primary amino acids. Okay? Proline is the only one that's secondary, meaning that proline bites back on itself. Okay? Where if you look at the other structures, it's acid, R group, amine, all the way through. Proline goes acid, R group, whoop, amine.
Yeah.
Okay? So it double binds to itself. The alpha position is a stereocenter. Very commonly, glycine is an exception because it doesn't have a stereocenter. Okay? That stereocenter is typically L. Did I get that right this time? Okay. Isoleucine and threonine contain a second stereocenter. So if you looked at the structure, you should be able to pick that up. That is one that if I asked it as a question, I would probably give you the structure and say, okay, what's going on with it? Because I don't expect you to memorize that as a useless fact. You do get uncommon amino acids. Those uncommon amino acids come from standard amino acids. They've just been altered their structure somehow. Okay, so there's, I think one table I was looking at had 21 amino acids, and it was a selenium structure. And I don't remember which amino acid it was a mimic of. But selenium replaced, I think, oxygen. Okay? And then your pKa's for the alpha carboxyl and the alpha amino. So you're responsible for those. Where this all ultimately ties into, which is how we shift into chapter 4, which I'll talk about too in a little bit, is that we now take all of these individual pieces, we put them into a larger extended structure, and we now have to interpret something about that extended structure. How is it going to interact with its environment or itself? Right? If it doesn't interact with its environment, what does it then do? Well, it's got to interact with something. It interacts with itself. What does that do to the overall shape of your structure? Okay, so we've got the pieces that we can then build into proteins.
You want us to memorize like 5 of amino acids, the structure, and then you also want us to know each of their 5 carboxyl pKa's and amine pKa's?
As long as you know the pKa is roughly 2 and of the alpha carboxyl and the alpha amine is roughly 9. Yep, just in general. Yeah, I think those are closer. I think those are the actual average for all of them. Again, 9 versus 9.5. That's actually starting to push on the threshold of being incorrect for an approximation, but it's close enough for anything that you would get asked. Okay. So the tail end of chapter 3 now says that we start to bind these to each other and we start to build our peptide chains. So we are looking at reacting 2 amino acids with each other in a fashion that now gets us to ultimately a full peptide. Right? So what happens in that reaction? Well, one of the things that we had already talked about, and this structure is nice and misleading, because when we go through and look at this, what charge do you expect the nitrogen to act as? It says positively charged. That looks a little weird. Because what does the nitrogen need to do in this reaction? Sort of. It needs to act as a Lewis base and share its electrons with our carbonyl to kick out the oxygen. So to do that, our free-floating amino acids, when they get hit into a situation where they have to synthesize, the structure or the enzyme will go through and shift those hydrogens around into their appropriate spaces to allow for the proper bond formation. Okay? In either case, the nitrogen must act as a nucleophile. Okay? It is what is supplying electrons. It is the electron donor in this case, regardless of what the free amino acid looks like. The carboxyl group must act as an electrophile, which is our electron acceptor. Okay. So we've got the nitrogen for our nucleophile, and we have the carbon of the carboxyl group acting as the electrophile, okay, to push this reaction along. That bond is officially an amide bond. Another thing that just drives me crazy on this. Biochemists didn't like organic chemistry so much that they decided to invent new names for bonds. Okay? Even though it's the exact same bond that you see in organic chem. They give you a peptide bond. Okay? The peptide bond they're trying to show here isn't super highlighted, but it's that bond. When we look at our structure, if we added some atoms over the top of this, we're looking at a carbonyl carbon with our bond to our nitrogen. That then goes to a carbon, then goes to a, to another carbonyl for our second amino acid. The other direction, it goes carbon, carbonyl carbon to nitrogen, which can then continue on. Our R groups will be off of that center carbon. I guess I shouldn't draw that in blue. Okay, whatever those may be. Okay. We also want to note kind of a standard notation here. If we go through and look at this, if I pick this structure and flipped it over, would I draw it exactly the same? No, so it doesn't have a symmetry associated with it. And if you look at all the peptide structures, you will always, always, always notice that the first atom that you see is a nitrogen. Okay? When we look at our peptide chains, we start with the amino end and we end with the carboxyl end. It is a standard notation. Okay? It's a simplification to hopefully make it easier to interpret your overall structures. Questions on that?
So nitrogen bonds with the carbon, it's losing one of the hydrogens?
The nitrogen will actually have to lose 2 hydrogens, which is what they're attempting to show in this figure without understanding any organic chemistry. So they goof a lot of it. So what they're saying is that we take out that oxygen, that hydrogen, blue over blue was a bad choice, oxygen, hydrogen, hydrogen. So that's what they're trying to highlight, is that those atoms are what are getting disappeared from the structure. Okay. How it does it, they're trying to ignore that fact as well. Okay? Other questions with it? Okay, so here's our wrap up all together. So we take all of this information, we put it all into one big file, and we end up with this fun question, which is something that is not in your slideshow first off, but is also a very valid test question for any other class. Given this peptide chain, and let's say an arbitrary pH, let's go ahead and say pH 7, also known as physiological pH, or close enough to it, what information can be determined? What is S? Searing. What pKa's are associated with searing?
Just 2 and
2 and 9. Okay. Why is that going to be important?
overall charge.
It can contribute now to the overall charge of this peptide chain. How? If I'm at a pH 5, what is the charge contribution from serine? So at a pH 5, what happens to our carboxyl group? Should it be protonated or deprotonated? Sorry, pH 7. I don't know why I keep saying 5. pH 7. Okay, the pH is higher than my pKa, which means you remove the hydrogen. What happens to the acid functional group then? The hydrogen's gone and its charge becomes negative. What happens to the alpha amino group?
Yeah. pK is above the pH.
Deprotonated, which means you remove the hydrogen and the alpha amino is what charge?
Is that right?
Wait a second. pH 7. So we got a pH 7.
Yeah.
Okay, so it would be protonated because your pKa is higher than your pH.
Yeah.
So it's protonated, so it would be positive. So what is the charge contribution from serine?
Overall neutral, 0.
Why are you shaking your head? No contribution. So we could say no contribution. It turns out it does have a contribution. That charge contribution for serine is positive. Why? There's another hint. There is no charge contribution from the acid.
Beginning of the peptide chain. So
Serine is on the left-hand side, which means the amino group is exposed. So its amino group needs to contribute. Where's its acid group? Buried in the peptide chain. It's no longer an acid, it is an amide. The amide is neutral. There is no charge associated with it. The charge contribution to the overall structure from serine is positive. Let's switch this up to the extreme end. T. Uh-oh. I don't know. T. Threonine? Cool. What do you mean you think so? I just committed to it. What's our pKa for our acid functional group?
2.2.
And our amino functional group?
9.11. But you have a third.
And pKa is for the third?
10.07. Let me make sure I'm going across the line right.
Oh yeah, threonine. We just did that, yeah. Okay. At a pH 7, what happens to our acid functional group? pH is higher than our pKa, so it should be deprotonated. So its charge should be negative. What happens to our amine functional group?
It's in the chain.
Okay, so there's a couple answers that we come up with there. I like the positive if it's just the free amine. But you have to remember again, where is the free amine on threonine? It's in the chain, which means does it contribute at all? No. What about the R group? It is going to contribute, or it's going to contribute some aspect to the charge. We now have to figure out what that charge is, okay, because it is a pKa that we now have to evaluate. It's not part of the chain, it's coming off of it. We take a look at that pKa, it's 10. So what does that mean as the protonation state? Protonated or deprotonated? Protonated. So what charge? Why is it 0?
Because,
Yes. Keep going.
well, because it's protonated, but it's on the structure.
You have to be aware of the structure of your amino acid. Threonine was an OH. If we keep the oxygen protonated, its charge is
0.
neutral. So the charge contribution from our threonine ends up being negative. So the question, if we just evaluated those two atoms, what would our overall charge be? 0. Because the positive cancels the negative, our overall charge is 0. We have a lot more amino acids through the middle of there that we have to go through and process. Okay? Sucks, but that's what you would have to go through and do. This is a perfectly valid question to see in a more advanced biochem class. I know for a fact that I've had to answer questions like this, and it sucked. Okay? This is why you needed to know the alpha group and the amino group, and then you tried to memorize those last 7 and hope you memorize them right. Okay? You can fully expect a question like this on the exam. You will have a much shortened peptide chain, right? And I will have to give you all of the pKa's. Okay? So it's a lot of stuff. It is also something that I know requires a bit of thought process and logic to get through, which means it probably wouldn't be a multiple choice answer, because the whole point of it is to see how you're thinking about it. Okay? So if you saw a question like this, you're looking at maybe 3 or 4 amino acids. Okay? And those would all be, the pKa's for all of those would be given to you.
What about the structure?
And the structures. Okay, so that's a glut of information. Glut of information questions typically have a low probability of showing up on an exam. Okay? Just because that's a lot of work I have to put in for a single question to get very little out. Okay? It does show up in your homework.
Yeah.
Okay, so you have to be aware of that. When we go through and take a look at any one of those middle amino acids, do I care about the alpha group or the alpha carboxyl buried in the peptide chain? Do I care about the alpha amino? No. So if I look up E, I don't remember what E was, but I'm pretty sure it's a charged one. I would just look at the R group pKa and evaluate that back to the pH. Remember, you have to have that pH. If you don't have that pH, we can't do any predictions about the charge. Is it? Yeah, what was it?
4.25.
R 4.25. So we would then have to evaluate what happens to it. Is it protonated or deprotonated? Does it carry a charge in that case? Okay.
What did you
And
say about the 10.07? That was another
That's
pKa
the
for them,
that's
and
the
another-
third pKa for threonine. It's R group. Okay. Its side chain has a pKa associated with it.
I was wondering that same thing, because on this one list right here, it doesn't have a number for the R group.
Did we look at it
I
wrong?
think we took the R group over.
Oh, tyrosine? Yeah. It's okay. So then it wouldn't have one, and our overall charge, oh, in this case, would still be negative. So sometimes you can get lucky. Okay. What is the one-letter code for threonine? Is it T? Oh, it is T. What's tyrosine? Oh, tyrosine's Y?
Tyrosine is
Oh, darn it. I could have spelled that right. Okay. So, chapter 4, all about intermolecular forces. So you're now taking these basic sequences from chapter 3, which relied on chapter 2, okay, And now we're moving to chapter 4. We have to take chapter 3 and chapter 2, because I think that's where we talked about forces, was in chapter 2. And we put that all together and try and predict something about how these chains, or these peptide chains, can now interact with each other to generate different shapes. Okay? Those shapes get subclassified depending on what you're looking at. So you end up with let's see, did I actually put it up here? No, I didn't. Okay. What we end up with is primary structure, secondary structure, tertiary structure, and quaternary structure. Each of those stages are moving up in complexity depending on what you're trying to look at. Okay. This section through secondary structure will be on the exam next Thursday. Okay, so you should read up on it. We will talk about it as kind of a review to make sure you guys are solid with that information when it comes down on lecture on Tuesday. Okay. There is a lot of true-false questions, and I would argue that chapter 4 homework is very, very challenging. I'm pretty sure I just pushed the due date on it, because it's not due before the exam. Because we're not going to get through the whole chapter, and there's a section in it on myoglobin and hemoglobin, the differences between those, that is really important for probably anybody taking a test, okay, in the future outside of this class. I'm not sure I like the textbook section on that material, so I'm going to do some research and see if I can't find a better way to describe it, and I will get you that reading material as well. It'll come, again, after exam 1, because that's after exam 1 material.
But the first and second structure.
Primary and secondary structure are on exam 1. As just a real quick overview, primary structure, we've already talked about. It's the sequence. That's it. Primary structure is what is the amino acid that you start with. So that's amino acid 1. What's amino acid 2? What's amino acid 3? That is primary structure. Okay? Very straightforward, very little information associated with it. Okay? What we saw right here is primary structure. Okay? So there's not a whole lot associated with our primary structure. Where it gets more complicated, and we'll talk about some effects of primary structure, is the secondary structure. Give me a better figure. There we go. We get two primary things coming out of I should have said important things coming out of secondary structure. You get alpha helices and you get beta sheets. Okay? The only reason we really talk about those is that when we were eventually able to see the structures of proteins, we noticed that there were these particular patterns that formed. So if you remember that video, I know I'm going backwards and forwards, the beginning of the semester that I showed for the ATP synthase, okay, this is kind of what we would refer to as kind of a globular thing, but even when you look at this, you kind of see some patterns here. For instance, if we look really carefully on that, you kind of see a line there, 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 there. You guys see that? Okay. That is due to secondary structure. That secondary structure happens to be an alpha helix. If we go through and take a look at the sections bound within that membrane, what they're referring to as the FO, you can see that same patterning. So what they ended up doing is when they looked at these structures, they saw these very similar patterns show up multiple times. Because these patterns showed up consistently, they started to evaluate them, okay, or call them different names. You get a different version of the alpha helix shown in both of those cases. Okay, so what they've done is animated and removed a lot of that atom information and just turned it into a ribbon so that we can see those interactions. Okay. The other thing, and I know I'm done, if we look really carefully way up at the very, very top, there, okay, ribbon, 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 line. Why did they show the line and not a ribbon?
Nice place bonding.
Ribbon is recognizing the alpha helix. That squiggly line is because it doesn't have a secondary structure associated with it. Okay? It's just a bunch of kind of random motion associated with it. So they can't really nail that down as a particular shape.
So that's just primary, it goes from secondary to primary?
It's not primary. As soon as you move into secondary, tertiary, or quaternary, there is no more primary. Primary is only the sequence of amino acids and nothing else. So even in that image where we saw that squiggly line moving around, if you got rid of the squiggle and just made it a straight line, then it's primary structure. As soon as you got the squiggle, it's not primary anymore.
They just don't know what it is?
It just doesn't have a regular shape.
Oh, okay.